Hello everyone, I'm Luca Zanolini and I will present you our joint work with Christian Cachan on revisiting signature-free asynchronous Byzantine consensus. In his work, we revisit the well-known randomized consensus protocol from Mustafawi et al. And we address a subtle Liveness issue while keeping its simplicity and its properties. Let's start by recalling the definition of consensus. Consensus, we mean reaching an agreement among multiple processes on a common value, despite unreliable communication and the presence of faulty processes. In his work, we consider Byzantine faulty processes. This means that processes may arbitrarily deviate from a protocol associated to them. Among asynchronous, randomized, and signature-free consensus protocol, the protocols from Mustafawi et al. Represent a landmark result, and they've been praised for their simplicity. In particular, the POTSI 2014 version is a signature-free consensus protocol that uses randomization, and this is addressed by the use of a common coin. It achieves optimal resilience, meaning that it tolerates until n/3 Byzantine failures, is round-based, and is constant in expecting running time. Moreover, this protocol, due to its simplicity, is suitable for application in blockchain networks, and in particular, for example, on a Badger BFT implemented it. The idea behind this protocol is the following. The randomized consensus uses an underlying binary validated broadcast to broadcast the values, and it uses a common coin to decide the final value. Let's see here a simple execution. Let's say I'm a correct process, I'm honest process, and I behave correctly. So I start to propose a value B. This value B is binary value, so it could be either 0 or 1. I start by BV broadcast, by binary validated broadcasting this value B. I deliver this value through a BV deliver event upon receiving 2f plus 1 times this value B. If so, then I broadcast this value B to everyone in an aux message. I wait until receiving at least n-f times this B from other processes and from myself also. At that point, I start to release the coin. I wait the coin to be reconstructed, and as soon as I reconstruct the coin, I check if the value that I received, the value B that I received, is the same as the value of the common coin. In this case, I decide for this value B. If this is not the case, so if B is not S, then I don't decide, but I broadcast. I start another round by BV broadcasting B for the next rounds. However, there could be another scenario possible. In particular, the possible scenario is that I could deliver both B and B prime. This means that I could broadcast to all, first an aux message containing B, and then an aux message containing B prime to everyone. This means that instead of only receiving B from at least n-f other processes, or B n-f times, I may receive a set B containing B and B prime at least n-f times. If this is the case, we have a modification in the final part of the protocol. If before we were checking B to be equals to S, if we receive a set B n-f times, at least n-f times, in this case, I don't decide. I just start a new round by BV broadcasting the value of the common coin. And this is an overview of how this protocol works. But let's see an example. Let's consider 4 processes, process 1, 2, 3, and 4. And let's consider P4 to be a malicious process. Process P1 proposes 0, while process P2 and P3 propose 1. So they start by BV broadcasting the value 0 here, the value 1, and the value 1. Here, we see where that process P1 receives 2f plus 1 value messages 1, in particular from process P2, process P3, and process P4. Process P4 is malicious, so can decide to send whatever message it wants. In this case, then, it delivers, process P1 it delivers message value 1, and it broadcasts an aux message to all containing 1. Process P3 instead receives value 0 from P1, P4, and I didn't mention before, but now I need to introduce this mechanism that is inside the broadcast primitive, and this includes that if I'm a correct process and I receive f plus 1 times a message with value b, then I will broadcast this b, other than broadcasting my original value. This means that here, process P3 receives value 0 from P1, P4, this is f plus 1, because f is equals to 1, we receive from 2, I broadcast to all the value 0, I receive also myself the value 0 that I just broadcasted. This means that I received value 0 from P1, P4, and P3, I deliver message 0, and I broadcast to everyone aux message 0. Moreover, I will also receive message 1 from P2, P3, and P4, again because P4 is malicious and it sends whatever it wants. So I deliver also message 1, and I will broadcast an aux message containing 1. Let's move on. Here, again, process P1 will receive message value 0 from P1, P3, and the P3 is from this amplification mechanism, we can call it like this, and from P4. And I deliver 0, and I start again by broadcasting to everyone also an aux message containing 0. This means that we don't have a single value, but you have a set B. We receive aux messages from P1, P3, and P4, and the same also for process P3. It receives from P1, P3, and P4. They both received n minus f aux messages, because n is 4 minus 1, 3, and they have the set B. The set B has been received at least n minus f times. This means that by following the procedure that I described before, what they do is they start to reconstruct the coin, and let's assume that the random value of the common coin is 0. So they will just broadcast in the next round, the new round, value 0. This by following the protocol. But what happens with process 2? Let's notice that by assumption, in the original formulation of the protocol, the adversary, the malicious process, can reorder messages and can delay the messages between correct processes. This means that, let's now analyze the situation with process P2, but we notice a liveness issue. The liveness issue is exactly given by what I just said, that adversary can reorder messages between correct processes and delays them. Let's recall this. So, let's move on with process 2. Process P2 will receive the value 1 from P2, P3, and the malicious process P4. The process P4 will delay messages that arriving to P2. So P2 will deliver 1, will start to broadcast aux message 1. It will receive an aux message from P1 and P4 from the previous steps that I described, and from P2. P2 will have this set B, will have this single value 1, will start to release the coin. The coin will be reconstructed with value 0, and there is the check. The check is the value 1 equals to the value of the common coin? No. So we'll broadcast the value B from the next round. As we can see, the next round then will start with process P2 broadcasting value 1, while process P1 and P3 broadcasting value 0. This procedure can be applied again and again and again by the malicious process, preventing termination. We show how to fix the problem. It's important to notice that A common coin is implemented by a protocol that exchanges messages among processes. This means that also during the reconstruction of the common coin, there is an exchanging of messages. And this is very important because if in some way we are able to take away the power of the adversary to reorder messages, then process P2 cannot receive processes from the protocol of the common coin before receiving the previous messages sent by the processes that are going to reconstruct for P2 the common coin. So the first change that we do to the protocol is by imposing a FIFO ordering on the reliable point-to-point links as in the original paper, including the messages exchanged by the coin implementation. What does it mean? It means that process P1 and P3 have sent two value messages and aux messages each before releasing the coin. This means that before process P2 receives the coin messages, we can call them like this, to reconstruct the coin, because of the FIFO ordering, first process P2 has to receive all the messages that have been sent from process P1 and P3. So P2 receives these messages from at least one of them before receiving enough coin messages. In this way, the adversary may no longer exploit its knowledge of the coin value to prevent termination, because this is the key part. The adversary is able to reconstruct the coin to know the common coin value before forcing P2 to deliver the opposite and starting this infinite loop that prevents termination. So what happens here is that here we no longer have only the set B containing only 1, because in this case, when we reconstruct the coin, before receiving the coin messages that will be used to reconstruct this coin, we receive also all the previous messages, as I already said. So for example, the aux message containing 0. This means that the set B should become 0 and 1, in the same way as for process P1 and P3. This means that then process P2 will start a new round by BV broadcasting value 0. And this solves the problem. However, the set B in the original formulation of this protocol is static. This means that as soon as we start to release and reconstruct the coin, this set B cannot change. What we allow with the second change is for the set B to dynamically change while the coin protocol executes. This means that here, if we start to release the coin and we start to wait for messages to be received from other processes, before receiving the coin messages, we start to receive the aux messages. And in this case, by allowing set B to be dynamic, this set B will change according to it. So, as soon as we finish to reconstruct the coin, we will have the set B containing 0 and 1, and we can start the next round by BD broadcasting the value 0. A final change is that we did that doesn't has an influence on the liveness issue, but our protocol does not execute rounds forever, as in the original formulation. However, this change doesn't have an impact on fixing the problem, on fixing the liveness problem. So I will avoid to discuss about it, but you can find everything, other details in the technical paper. So this concludes my presentation. Thank you very much for your attention, and I invite you to read the blog post, the detailed blog post that we wrote, or to read our technical paper. Thank you very much.